it is time to learn your first big tool with integration, the method of substitution. Okay, let's take a look at some examples so that you can understand how to use the method of substitution. And the idea here is to make your life easier, okay? So let's start with an example. Let's say we want to just get the integral of the sine of 2x dx. Okay, so you might be able to figure this out without using substitution, but let's use this as an example to illustrate how it works. The idea is you want to substitute in another variable to make your life easier. And you often want to think about, what can I substitute in, say for some variable u, so that when I make the substitution, I have an easier integral. Well, we know what the derivative of the sine of x or the sine of u is, so it makes sense that we would say u equals 2x. Now, the key here is that there's a second part, and that's the dx, because you have to deal with that also. If you're going to change to u, you need to change to du. So what we do, you take the derivative of your new variable, and you say du equals, derivative of 2x is 2, and using Leibniz notation, you write the 2 dx. Okay, so this is good. So now if you start substituting in, okay, you've got the sine, you switch your 2x out with a u, but now what do? Because you've got this dx equals, well, you don't have what dx equals, that's what you want. You've got du is 2 dx. If you had a 2 dx, that would be fine. So in effect, what you need to do is solve this for dx, right? Your 2x is there, boom, u. But you don't have a 2 dx, you just have a dx. So you want to move the 1/2 to the other side. You get 1/2 du equals dx. That's what you substitute in, because that accounts for everything. So you put your du times 1/2, you can move the 1/2 here. In effect, it can even go out in front of the integral. Now, we have just what we want. Derivative of sine is negative cosine, integral. Negative cosine of u, and we got the 1/2. I'll just put it like this, 1/2. Okay, great, but the problem was given to you in terms of x, not in terms of u. So what you need to do then is make a final substitution, and here you could say, all right, well, I want to go back in, u is 2x, and that's your final answer. It's negative 1/2 cosine of 2x. Now, if you check this one, meaning like you start with this and you take the derivative, again, the negative 1/2 can come out. What's the derivative of cosine 2x? Cosine is negative sine, the negatives would cancel. You get sine 2x, but by the chain rule, it is times 2. And that times 2 would cancel with this 2. And so you will, in fact, get sine of 2x. The method of substitution is sort of like an inverse chain rule. Okay, so let's look at another one. Okay, with this number 2. What would be the integral of e to the x over 1 plus e to the x dx? Okay, it's a little bit interesting. Now, you've got to think on this one for a little bit. It's kind of tricky. Okay, so what might u be? Could u be e to the x? Maybe. And I mean, you could try it. Okay, if you get u over 1 plus u, can you integrate u over 1 plus u? Ooh, I don't know. What else might you be able to try? Okay. The e to the x is actually helpful. And so you could think about, well, what if u is 1 plus e to the x, right? Your denominator, whole denominator. If you just had 1 over u, the integral would be natural log of u. So if we say u equals 1 plus e to the x, then what's du? Du is e to the x dx. Oh, and that's actually helpful because that is the numerator. right? So there's the denominator, there's the numerator. It can all go up in terms of then x dx, that's du. The denominator is just u. Okay, that's really nice. That's simply the natural log of u. Okay, great. What other examples, might be useful? Okay, so let's try another one. And let's consider the following. Let's consider 3 integral of, now we're going to go with sine squared x times cosine of x dx. Okay, so again, with your substitution, the goal is like, what is u? How do we figure out what u might be here? You could try something like u equals sine squared of x, okay? And then if you do that, let's write it out. Okay, so u equals sine squared of x. Now what's du? Du is 2 sine x, but by the chain rule, this would be times cosine of x. And you can see, like, already, you end up with too much because, if you start to plug in, you got the u, but then you've got an extra sine x there, so it's too many. And that's what'll happen, like, when you're wrong. It'll often be like you have too much or not enough. Okay, so u equals sine x maybe is not the best choice. Okay, so what else could we try? U equals what? Now, I think the key is about, in both cases here, just thinking about what is du, right? And so du is what's going to help you. And so if you try this, u equals just sine of x without the square, well, now du equals just cosine x dx. And that's exactly what you have over here. Okay, so that's really good for the du. And sine squared is simply u squared. So this is a great substitution because now you get, it's just u squared, that's the sine squared du. And so now you can get that as, that's u cubed over 3. But what's that equal to? It's sine cubed x over 3, because u is sine of x. And so just to look at this one, so like if you start to plug back in, you take the derivative, right? It's the derivative is actually, okay, it's a power function, so the 3 comes down, those 3's cancel, you're left with sine squared x, but by the chain rule, it's times the cosine of x, okay? So the sine squared of x is it's more difficult to integrate when there's not a cosine x. And that's what you're seeing as a pattern here, is it's actually helpful to have an extra piece often because of the chain rule. Okay, let's look at one more example. Okay, how about the following? Now, in this last example, we're going to add something to the mix. Okay, what we're going to add here is, we're going to add bounds to this. And we're going to say that the bounds go from 0 to 1. And then what we're going to take the integral of is the square root of 3x minus 1 dx. Okay, so you just think to yourself, what should you be to make your life easier? Now, and you also think, what can you integrate and what's du? So for me, I naturally, like when I look at this, I think, okay, it's going to be simpler if like I just say u equals 3x minus 1, because I know how to integrate the square root of u. Furthermore, du then is just 3, and like in this first problem, anytime you have a constant number, that's fine, you can work with that. So what we'll say is u equals 3x minus 1. You wouldn't do like u equals root 3x minus 1, because that's exactly what you have. And then you'd say du equals just 3 dx. Okay, so now, this is interesting. The reason why it's interesting is because of the bounds, okay? So let's come back to the bounds. Just write the integral. Now it's the square root of u. Now this 3, it's du is dx with the 1/3, it's like 1/3, right? 1/3 du equals dx. So you can pull out the 1/3, and then it's just du. Now, I said, what about the bounds? Here's why. These bounds are in terms of x, not u. So you have 2 choices. Choice number 1, you can actually fix the bounds now. And you can say, okay, I've shifted into the world of u, and that's where I'm going to stay. I can actually substitute these in, and I can say, okay, if x is 1, that's 3 minus 1 is 2, and then if it's 0, that's -1. Okay, so now I'm in the world of u, and I never go back to the world of x. You can definitely do it like that. That's one way, okay? So if we do it this way, I just got to integrate u to the 1/2, right? That's u to the 1/2. If it's helpful, you can write it again, right? U to the 1/2. Maybe I'll write it again, right? So this is 1/3 to -1, u to the 1/2. And so now when I integrate, I in fact add 2 halves, because you add 1 to the power. I get that's u to the 3 halves. And if it's over 3 halves, that's times 2/3, but you already have a 1/3 there. So 2/3 times 1/3 is 2/9. And evaluate at these 2 points, 2 and -1. Okay, now this is interesting because we actually came up with bounds. I put the 0 in there, but the bounds are actually undefined at that point. Okay, so really it would only be defined where it actually becomes positive. Okay, and typically in calculus you can be given problems where you won't have to deal with that. So I'll just make everyone's life a little easier and say, let's just make this a +1. And then everything in the domain is okay, but the bounds would change, right? Because if it's +1, then suddenly it's not going to -1. It's going from 3 times 1 is 3, plus 1 is 4, 4 to 1. Okay? So you could say that's a little bit of my mistake. You can still do it, but we're gonna avoid complications like that for now. And so what we do then, we just say this is from 4 to 1. And same thing here, evaluate at 4 to 1. Okay, so let's actually evaluate at the points and see what we get. Okay, so the square root of 4, so 2 to 3 halves, you could take the square root. For square root of 4 is 2, 2 cubed is 8, that's 16/9. Minus 1 to 3 halves is just 1, 2/9. And we can see that we get 14/9. Now, let's just go ahead and do it the other way so that you can see how that would work. So, alternatively, you could say, okay, I don't want to change bounds. I want to keep it. I want to just say this is 1/3. We started with 0 to 1. And what I'm going to do is I'm just going to go forward, but I'm going to actually put everything back in terms of x. Okay, so you could do it like that too. Let's see how that might look. Okay, well, you do your integral. It's the same integral, right? U to the 1/2, it's going to be 2/9 u to the 3 halves. Evaluated at 4 and 1. But evaluated at 1 and 0, because you're keeping it and those are x's. And so if you keep it at 1 and 0, it's fine, but you've got to go back and put in what the x is. And so you can see the x is, that's 2/9, 3x plus 1. Now you go back to 1 and 0. Now, what's interesting about doing it this way is you can see it actually doesn't make a difference, because when you plug in the 1 here, what do you get? You get 4, which is what you plugged in here. And so you get the 4, when you plug in 0, you get the 1, right, which we have here. And so it's still going to give you the same result, the 16/9 minus 2/9, as it should. So the advantage, I would say, of doing it basically this way is that when every statement is true, this is not actually true. If you start with this integral and you're over here, it's actually not the integral from 1 to 0 of the square root of u. What you're saying is, and it's okay to do this. Okay, I'm gonna hold off. I'm gonna go back and put it in terms of u. You can even call those 1 and 0, maybe even something different. And then it becomes exact, once again, right here, because it's in terms of x's. Okay? So, students do it typically both ways. You can sometimes depend on the problem, but it can be kind of nice to emphasize substitution, to go with u, stay in u, and live in the world of u. Right? So just to recap this one, the method of substitution is the following. You choose a change of variable. Pretty much everybody uses u. And you do that to make the problem easier so that when you do the integral, it's something you can do. Right? Like it's not clear what the integral is here, perhaps. In each of these cases, I do want to mention, you might be able to see it outright. Because if you can see, oh yeah, I know, it's negative cosine of 2x, but by the chain rule I don't have the 2, so to compensate for that with the 1/2. Similar to this one, you're going to compensate for it with the 1/3. This one, if you could see that, oh, the derivative of the denominator is the numerator, it's just ln of the denominator, right? ln of u. Oh, and that one, by the way, I did the thing I'm not supposed to do. You're not supposed to leave it in terms of ln u. Right? It should be ln 1 plus e to the x. It's the same difference if you make a substitution, but if the problem starts in x, you should finish it out in x. And then you see ones like this too, where it might be like some power, but then you need the other piece because of the chain rule. So it's a great tool. It's designed to make your life easier. Just make sure you account for everything when you do the du part and the dx.